Welcome back to the Algebra 2 Structure and Method textbook series. This lesson is written based on Chapter 8, Section 2, which is on inverse and joint variation. So today we're going to solve problems using joint variation and inverse variation. You should know how to solve radical equations and solve quadratic equations. You should also feel somewhat comfortable with direct variation. It's going to come in handy. You'll learn a couple of new words. For our warm-up, we need to substitute values into the following expressions and find the value of k. And take care with your order of operations. I'm going to show my answers in 3, 2, 1. There. Okay, if you struggle with this skill, review the lesson from Chapter 8, Section 1. Let's get started with inverse and joint variation. You might recall that the distance traveled by an object is the speed times the time traveled. Suppose we hold the distance constant, that is, it can't change. What is the relationship between the rate and the time? Well, if the rate of speed increases, then the time to travel the distance will decrease. So, for example, a runner in a 100-meter race, the greater the speed of the runner, the less time it takes to complete the distance. So let's consider that new equation in our 100-meter race. Our formula becomes 100 equals RT. If we isolate time, our equation becomes T equals 100 over R. This relationship is called inverse variation, and we say that T varies inversely as the speed R, where 100 would be our constant of variation. It's a number that doesn't change no matter what happens with T and R. So let's formalize this a bit. When a function can be written as xy equals k, or y equals k over x, where both x and k are non-zero, the relationship is called inverse variation. It's a fixed value, k is a fixed value that we call the constant of variation or the constant of proportionality. This relationship can also be stated as y varies inversely as x and y is inversely proportional to x. The graph of inverse variation is something that you're going to learn more about later in parent functions. But it's the positive portion of a parent function that we call the reciprocal function. The graph is nonlinear and decreasing. That means that as x increases, the value of y decreases. So in example 1, y is inversely proportional to x, and y equals 6 when x equals 5, and we need to find x when y equals 12. This is a very typical inverse relationship problem. We take our given information, we find k, and then we solve for one of the quantities. So let's get started. First, I'm going to set up the variation equation. Y is inversely proportional to x is y equals k over x. Then I'm going to substitute x equals 5 and y equals 6, so I can solve for my value of k. So k equals 30. Now I'm going to take that value of k and plug it back into my original equation, so I get y equals 30 over x. Now, I need to find out what x is when y is 12, so I'm just going to substitute y equals 12 in and solve for x. Okay. When a quantity is linked as the product of two or more quantities, the variation is called a joint variation. The function can be written as z over xy equals k, or z equals k times x times y. That's the one we're probably going to use the most. This can also be stated as z varies jointly as x and y, and z is jointly proportional to x and to y. Let's do an example for some clarity. So for example, if z varies jointly as x and the square of y, then we can say that z equals k times x times y squared. Another example would be z varies jointly as x and the square root of y, then z equals k times x times the square root of y. Sometimes the hardest part is just getting the actual equation set up, but once you get good at that, you're usually in great shape. Okay, so example 2. We're told that z varies jointly as x and the square root of y, and z equals 6 when x equals 3 and y equals 16. And we need to find z when x is 7 and y is 4. So our first step, again, is to set up the variation equation. It varies jointly as x and the square root of y, which is the same as the second example we just saw. Now I'm going to substitute for z, x, and y, and solve for k. Then I'm going to put that back into my original equation. And then finally, to find z, I'm going to plug in x equals 7 and y equals 4, and I get that z equals 7. Inverse and joint variation have many applications in physics and other sciences. For example, Newton's law of gravitation measures the force of attraction between two spherical bodies. Formally, the law is stated as the force of attraction between two spherical bodies varies jointly as their masses m1 and m2, and inversely as the square of the distance r between their centers. Okay, so based on the formula, or based on the law, do you think you can write the formula? If so, give it a try. I'm going to start now. The force of attraction F varies jointly as mass 1 and mass 2, so times m1 times m2, and inversely as the square of the distance r, so over r squared. Hopefully you got the same answer. In our final, very wordy example, we have direct and inverse variation. Told you it would come in handy. The electrical resistance of a wire varies directly as its length and inversely as the square of its diameter. 100 meters of a wire with diameter 6 millimeters has a resistance of 12 ohms. 80 meters of a second wire of the same material has a resistance of 15 ohms, and we need the diameter of the second wire. Boy, there is a lot there. The first thing we have to do here is we need to figure out what quantities are involved, and we need to state our variables. The first thing is I know resistance is R. I'm going to make my length of the wire L and the diameter of the wire D. Now that I have my variables, I can state my variation equation. So the resistance varies directly as the length and inversely as the square of the diameter. Hopefully you got that. Now let's substitute the information given to us in the second sentence and solve for k. So r is equal to 12, L is equal to 100, and our diameter is 6. Solving for k, I get 4.32. I can put that back into my original equation, and now I've got something that I can use to find any value of r, d, or L. 80 meters of a second wire of the same material has resistance of 15 ohms. So that means 15 is equal to 4.32 times 80 over d squared. Then I do some fancy math, isolate d, and I get 4.8. Great job today. I hope that direct variation and inverse variation are starting to sink in a little bit. Now turn to your partner and compare and contrast direct and inverse variation. I will see you in the next lesson.